Payment confirmations returned success, but records were missing from the database. Users were charged, orders showed unpaid. The root cause? A Cassandra cluster with n equals 3, w equals 2, r equals 1. During a network partition, a write succeeded on 2 nodes in one partition, but a read hit the single node in the other partition that hadn't received the write. R plus w equals 3, n equals 3, so the condition held, but the read quorum didn't overlap with the write quorum. The read returned no data, and the app retried, causing duplicate charges. Here's exactly why. Welcome to TheCodeForge. Before we dig into that production issue, let's cover quorum R plus WN. Quorum R plus WN is a consistency condition where the sum of read and write quorum sizes exceeds the total number of replicas. This guarantees at least one node overlaps between reads and writes, ensuring strong consistency in the absence of failures. The quorum condition R plus W N mathematically guarantees that any read quorum and any write quorum will intersect in at least one node. This intersection means the read will see the latest write, assuming the write completed successfully. Here's a simple simulation. With n equals 3, w equals 2, and r equals 2, the write quorum includes nodes A and B, the read quorum includes B and C. The intersection is node B, so the read sees the latest write. If r equals 1 and the read quorum is just C, there's no overlap, leading to a stale read. The choice of R and W depends on your workload. For a read-heavy system, you want low R to reduce latency, but high W to maintain consistency. For a write-heavy system, low W for fast writes, but high R to guarantee reads see the latest data. Here's a production configuration for n equals 5. For a balanced workload, set both R and W to 3. For latency-sensitive reads, you can use R equals 1, but be aware you might get stale data. For critical writes like payments, use W for maximum consistency. In production, nodes fail. If a write quorum cannot be achieved, the write fails. This is a feature, not a bug. You can use hinted handoff to store writes for temporarily unavailable nodes and replay them later. For reads, you can fall back to fewer replicas, but that returns potentially stale data. Here's a simulation. With one node down, the write quorum is still achieved. But if 2 nodes are down, the write fails. Hinted handoff stores a hint on the coordinator to replay when the node comes back. Quorum R plus WN is a consistency mechanism, but it's not a silver bullet. Under network partitions, the guarantee breaks. If a partition isolates a subset of nodes, a write quorum might be achieved in one partition and a read quorum in another, with no overlap. This is the CAP theorem in action. In a partition scenario with n equals 3, w equals 2, r equals 2, writes succeed in the majority partition. Reads in the minority partition fail because they can't achieve r equals 2. If you allow reads with r equals 1, you get stale data. The decision is to fail reads to maintain consistency. To maintain consistency over time, distributed databases use read repair and hinted handoff. Read repair occurs when a read detects that some replicas have stale data. It updates them in the background. Hinted handoff stores writes for temporarily unavailable nodes and replays them later. Here's pseudocode for read repair and hinted handoff. Read repair updates stale replicas asynchronously. Hinted handoff stores a hint on the coordinator if a replica is down and replays it later. Quorum R plus WN is not the only consistency model. You might choose eventual consistency for high availability or linearizability for strict ordering. In production, I recommend using quorum for all writes and reads that affect critical data and eventual consistency for non-critical reads. Here's a hybrid approach. In a checkout service, use quorum for inventory and order writes to ensure strong consistency. For recommendations, use R for low latency, accepting that data may be slightly stale. This is the same issue we highlighted at the start. Here's exactly why that happened. The cluster had n equals 3, w equals 2, r equals 1. During a network partition, a write succeeded on 2 nodes in one partition, but a read hit the single node in the other partition that hadn't received the write. R plus w equals 3, n equals 3, so the condition held, but the read quorum didn't overlap with the write quorum due to the partition. The read returned no data, and the application interpreted that as payment not made and retried, causing duplicate charges. The fix was to change R from 1 to 2, making R plus W equals 4, N equals 3. This forced reads to contact two replicas, ensuring overlap even during partitions. Also added read repair on every read to propagate the latest version. This resolved the incident and prevents recurrence. I once saw a team set R equals 1 and W equals 1 for maximum availability during a partition. Every node accepted writes independently and reads returned local data. When the partition healed, they had conflicting versions with no resolution strategy. Data loss was inevitable. Never set W equals 1 in a system that requires consistency. I've seen a billing system use W equals 1 for performance and then lose transactions when the single replica went down. The write succeeded on one node, but the read quorum never saw it. Disabling read repair to improve read latency is dangerous. You'll accumulate stale replicas, and eventually a node failure will cause permanent data loss when the only copy of the latest data is on a dead node. The hook incident was caused by setting R. This is a common mistake. During a network partition, a read quorum of one node may not overlap with the write quorum, leading to stale reads or missing data. Always ensure R plus WN and consider the impact of partitions. The article uses R equals 2 and W equals 2 as examples, but in Cassandra, consistency levels like quorum are computed as floor n/2 plus 1. For n equals 3, quorum equals 2, but for n equals 5, quorum equals 3. Always use the symbolic level, e.g., quorum, rather than hard-coding numbers, as the actual value depends on the replication factor and can change with topology. The article mentions multi-data center setups in passing, but doesn't show code. In Cassandra, local quorum ensures quorum within a single data center, avoiding cross-DC latency. This is critical for systems that need strong consistency without the overhead of global quorum. The article mentions hinted handoff, but doesn't warn about the default timeout, e.g., 3 hours in Cassandra. If a node is down longer than the timeout, hints are dropped, leading to permanent data loss. Always monitor hint counts and set an appropriate max hint window in MS based on your recovery time objectives. To diagnose quorum issues, first verify your R and W configuration. Then check for network partitions using cluster health tools like node tool status. Ensure read repair is enabled and running. Monitor the hint backlog to detect persistent node failures. Let's run through some common interview questions. What is the quorum formula and why is it important? R plus WN ensures read-write overlap for strong consistency. How does quorum behave under a network partition? Only works within a partition. Minority partition may fail operations. What happens if R equals 2, W equals 2 in a 3-node cluster and 2 nodes fail? Writes and reads fail because quorum cannot be achieved. And a few frequently asked questions. What does R plus WN mean? Sum of read and write quorum sizes exceeds total replicas, ensuring overlap. What's the difference between quorum and eventual consistency? Quorum provides strong consistency. Eventual allows temporary stale reads. How do I choose R and W? Start with R equals W equals quorum, floor n/2, plus 1, then tune based on workload. To recap, quorum R plus WN ensures strong consistency, but only when the system is not partitioned. Tune R and W based on your workload. Always enable read repair and hinted handoff. Start with quorum for everything, then relax to eventual consistency only for non-critical paths where staleness is acceptable. Ready to go deeper? Up next, distributed transactions and 2PC, then distributed locking, then consistency models. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.